it's time to start talking about a special case of solutions. There are special kinds of solutions known as acids and bases. And when we talk about acids and bases, we also need to bring up two related concepts. And that would be pH, which you probably have heard of in other classes, and a specialty technique that we use in the lab called titration. So let's just review very quickly. For the intents and purposes of this particular course, we're going to consider an acid to be anything that starts its chemical formula with H. So it very much so has a hydrogen ion in the front of it that's easily identifiable. A base, we're also going to kind of simply define in this course as anything that's going to end in hydroxide or OH. Some good examples to kind of just refresh your memory might be HNO3, nitric acid, H2SO4, sulfuric acid, HF, hydrofluoric acid, or HI, hydroiodic acid. For bases, again, the big thing that they're going to have in common is they all end in OH. So we have potassium hydroxide, calcium hydroxide, or lithium hydroxide. Now, we're going to limit our scope to the acids and bases that are going to be marked with the state symbol of AQ. So they're only going to be the aqueous species. And remember that what it means to be aqueous is that you dissociate when you hit water. Dissociate means you break apart into your ions. And when we do that, we really start to need to think about dissociation equations, or an equation that actually shows this chemical breaking apart into its ions. Now, the reason that we need to do this is because this is kind of the gateway into calculating pH. So here's an example. Here we have this cute little acid, nitric acid. It's marked as AQ, and it's going to want to break apart into its two ions, H and NO3. But there's a little bit of a problem, and that's that hydrogen ion. Now, hydrogen, the atom, is made from one proton and one electron. And when we make it into an ion, that electron is removed. So hydrogen ion is the same thing as just saying one proton. Now, one proton running around in your solution is not exactly the most stable of creatures. So this is a bit of an issue when we're talking about acids and dissociation. H1 plus actually doesn't even exist in solution. It's kind of a myth. What actually happens is this H1 plus kind of seeks out a bigger buddy so that it's more comfortable, more safe inside of the solution. And that is H2O, the solution itself. H1 plus, the proton, hydrogen ion, will kind of ride on the back of H2O, kind of like taking a little piggyback ride, and become this mysteriously amazing ion called hydronium. So when we talk about acids, we usually talk about this hydronium ion in the same breath. Now you can kind of see my equation doesn't look quite right yet because I just added a full H2O onto the product side. So I'm going to add one also over onto the reactant side, just to keep everything all nice and balanced. Now, one thing to be kind of very, very, very sure of here is that notice how many hydrogens I have in my nitric acid. Only one. I only needed to add in one water to make it all work, and that formed one hydronium. So for every one H that's in your acid, you're going to form one hydronium. And that hydronium is what makes an acid an acid. Let's swap out our acid. How about H2SO4? Now in this case, each individual H that comes off of that H2SO4 can make a hydronium ion, an H3O1+. So if I can make two hydroniums, I have to add in two waters to make this work. Now, at the honors level, you will not need to write these equations. At the AP level, you will. So if you're planning on moving forward with your studies, this is kind of an important thing to take note of. And again, at the honors level, you will not need to know how to write these equations. Just simply know the relationship between the H's and the acid itself. So there's two H's in every H2SO4. Let's take a look at the base equivalent. So a base dissociation equation is a little bit more of a simple thing. If you have something like KOH, which is marked as being aqueous, it will simply break apart into its ions, K and OH. Now because these are both large and fairly stable ions, They don't need to react with anything. They don't need to bond with anything. They just simply fall apart into the solution. So they're usually pretty simple. But again, you got to be really careful because every once in a while you'll get a wacky one like CaOH2. Now when he falls apart, he'll fall apart into one calcium ion but two hydroxides. And it's again that hydroxide part that makes a base a base. So what the heck is this thing called pH? Well, believe it or not, pH is an actual measurement of a concentration, and it's specific to acids. Many other people will also say that pH is a measurement of the strength of an acid specifically. Now, we have a specialty scale for it, and I know there's a lot of information on this one, but you might want to pause and take a moment to kind of look at this and see everything that's on here. You can see that the top of the pH scale is at 14, and the bottom of the pH scale is at 0, with the number 7 being smack dab in the middle. Now, pH of 7 is neutral. It's usually the pH of pure distilled water. Anything that would fall above 7, and notice some of the things that are actually listed on that list, including soap, it usually has higher pH. Bases have high pH. Anything below a pH of 7 is actually known as being acidic. So you'll see your juices, coffees, vinegar, even hydrochloric acid is listed on this list. Now what's interesting, take a look at how the concentration relates to the pH scale. It's actually a power of 10 difference in concentration to go from one pH level to another. So if you're taking a look at, say, like where soda is at a pH of 3 and coffee is a pH of 5, there is a 10 to the second difference in the concentration of the acid in those two materials. That means that one is actually 100 times more concentrated than the other in the amount of acid. That's why you have to be really careful when you're drinking soda. It's horrible for your teeth. Now, just like we have a pH scale, we also have a scale that measures the strength of bases. And it's a little less common, but it's still pretty helpful when you need it. It's called the pOH scale. Now, this one is kind of wacky. It's the flip-flop of the pH scale. It again runs from 0 to 14, but notice how the numbers are different here. Your bases have the low numbers. They're from 0 to 7, and your acids now are all of your high numbers. They're above 7, but they still fall in relatively the same place. Now, before we get into actual pH calculations, there's another little piece of information you need to know, and that's this weird kind of, this chemistry code. Chemistry code is kind of weird. We have a lot of weird symbols. One of them is square brackets. Square brackets actually conveys something very important in chemistry, and since we've been learning about it in this chapter, it's time that you know. Square brackets can translate in chemistry to molarity. So anytime you see square brackets around a number, and particularly if they're talking about a certain substance, they're referring to its concentration, its molarity. All right, so on to some pH calculations. So there's a formula for calculating pH, and that's simply this. pH equals the negative log of H3O1 plus. And before your brain shuts off because you just saw a log, because I know that that's everybody's favorite calculation, let's take a look and see what this looks like in an actual sample calculation. So here it is. What is the pH of an HCl solution that has a concentration of 0.010 molar? Time to get out the old handy-dandy calculator, and we're going to push some very special buttons here. First, I'm going after that negative button. Then I'm going to push the log button. And then finally, I'm going to type in the actual number for the concentration of that acid, 0.010. And now I'm ready to hit enter. And the calculator will give us our answer, and the pH of this solution is 2. That's pretty easy, right? Well, I'm hoping so. Notice how many H's are in the formula of our acid. It's HCl, 1 H. So that concentration is completely okay to use, but that's not always going to be the case. Take a look at our second example. What is the pH of an H2SO4 solution with a concentration of 0.010 molar? Well, in this case, Again, we're going to get our handy dandy calculator, but before we go to our calculator, I notice that there's 2 hydrogens in this acid. And really, H3O1 plus, remember, that's code for H, or how many H's I've got. I have 2 H's in this acid. That means I'm going to have 2 hydroniums for every 1 acid, and that's the concentration I'm after. So if my concentration of H2SO4 is 0.01, that must mean that my concentration of hydronium is 0.02, or double. Now, if you want to see this in multimole ratio form, you see that there's 1 mole of H2SO4 for every 2 moles of H3O1 plus. If we take a look at the stoichiometry of it, if you simply put down the molarity, 0.01 moles over 1 liter, and then apply the multimole ratio of 2 moles of hydronium to every 1 mole of H2SO4, you will arrive at 0.020 molar. So now we can go to our calculator. And again, I'm going to push negative log and then put in that concentration, 0.020, and hit enter. And my final answer comes out to be 1.7. So here I know that my final pH is 1.7. Well, anything that can be done can also be undone. So we have a reverse equation that will use pH to go back to concentration. And here it is. If you want to know the concentration back, you can take 10 raised to the negative pH, and that'll give you the information that you're seeking. Back to a sample calculation. What is the concentration of HCl with a pH of 1.5? Back to the handy dandy calculator. We're going to type in 10 to the negative 1.5 and hit equals. And my answer comes out to be 0.032. So in this case, I know that my concentration of HCl is 0.032, and that's only because there's only 1 H in it. If there was more than 1 H, we'd have to do something a little bit special, like here in our second example. What is the concentration of H2SO4 with a pH of 1.5? Well, I'm still going to go to my calculator first. I don't really have a choice. So 10 to the negative 1.5 is 0.032. Now that is the concentration of hydronium, but notice my acid again has 2 H's. That means I need to kind of trade it in a little bit. Here's the dissociation equation, just in case you needed to see that, where we have a 1 to 2 molar ratio. So I'm going to show you the stoichiometry this time. I'm going to take that 0.032 molar, or moles per liter, and trade it in. Moles of hydronium exchanged for moles of H2SO4. And that should give me my final concentration of 0.016. Now there's a whole bunch of pH calculations which can provide some very helpful information. Because pH and pOH are kind of analogous scales, they go hand in hand, a lot of the equations will allow you to interconvert between a bunch of these different numbers. So generally speaking, if you have one number, like H3O1+, you can calculate everything. You can calculate pH, you can calculate pOH, you can calculate OH1- concentration. You just have to be careful with the equation that you pick. My favorite equation is actually the second to the last, and that's simply this: pH plus pOH equals 14. It's a simple but easy calculation, and it's used pretty frequently in this class and also in the classes to follow. You might want to pause on this screen, make sure that you make a note of all of these calculations, and then try some out for yourself. Good luck!